The number that appeared on NOAA's Space Weather Prediction Center forecast page was 70, not a temperature, not a percentage of rain. A 70% probability that the sun would produce a radio blackout severe enough to silence high-frequency communication across the entire sunlit side of this planet. That forecast, issued for April 27th, April 28th, and April 29th, 2026, was attached to a specific culprit, two specific culprits, designated active region 4420 and active region 4425, both sitting on the Earth-facing disk of the sun, both carrying the most dangerous magnetic classifications that solar physicists assign to sunspot groups, and both demonstrating in the days leading up to that forecast that the classifications were not bureaucratic caution. They were earned. Region 4420 alone produced an M6, zero flare on April 26th at 22:57 UTC, reaching the R2 moderate radio blackout level, and that flare came with a Type 2 2 radio sweep measured at 834 kilometers per second, which is the acoustic shockwave moving through the solar corona ahead of a coronal mass ejection. By April 27th, NOAA had also assigned a 25% probability of R3 or greater blackouts, which is the classification associated with X-class flares, the most energetic category on the scale, 1 in 4, from a sun that had already days earlier on April 24th produced not one but two X-class flares within hours of each other. An X2, 4, and then an X2. 5, the second of which sent a Type 2 radio emission racing outward at 1,169 kilometers per second and caused immediate radio interference across the Pacific, Australia, and East Asia. But that is not even the real story, not even close. The real story is not the 70%. The real story is not AR4420 or AR425 as individual sunspot groups producing individual flares. The real story is what these two regions reveal about where we are in the life cycle of the current sun, about the system that produced them and the system that is sustaining them, about the reason that the declining phase of solar cycle 25 is generating active regions of this magnetic complexity at a moment when most people assume the solar maximum is behind us and the danger is fading. It is not fading. And the data that NOAA's instruments are gathering from the Earth-facing disk of the sun right now, cross-referenced against the behavior of this specific solar cycle across its entire active period, tells a story that goes far beyond any single forecast percentage. It tells the story of a sun that has spent the better part of 2 years building magnetic configurations of extraordinary complexity, that has now crossed its peak but has not lost its capacity for extreme events, and that is currently pointing two of the most combustible sunspot groups of the entire cycle directly at the 8 billion people on the lit side of this planet who depend on the electromagnetic environment that solar flares disrupt without warning and without apology. Let us start with what a radio blackout actually is, because the phrase has become common enough in space weather reporting that it has lost the weight it deserves. And restoring that weight requires understanding precisely what the sun is doing to the upper atmosphere when it fires a flare. The ionosphere is the layer of Earth's atmosphere extending from roughly 60 kilometers to 1,000 kilometers above the surface. It is not empty space. It is a region where the sun's ultraviolet and X-ray radiation ionizes the atmospheric gas, stripping electrons from atoms and creating a plasma, a sea of free electrons and ions that reflects radio waves the way a mirror reflects light. Every long-distance high-frequency radio transmission, every shortwave signal, every HF aviation communication, every emergency frequency that ships at sea use to contact each other across open ocean, every backup communication channel that governments, militaries, and disaster response organizations rely on when satellites fail or fiber cables go dark, uses the ionosphere as its transmission medium. The signal goes up, bounces off the ionosphere, and comes back down thousands of kilometers from where it started. That is how high-frequency radio works. That is why it matters. And when a solar flare erupts, it releases an X-ray pulse that travels at the speed of light, reaches Earth in 8 minutes, and slams into the sunlit side of the ionosphere with enough energy to massively over-ionize the D layer, the lowest part of the ionospheric structure. The D layer, instead of reflecting radio waves, begins to absorb them. The signal goes up and does not come back. The mirror turns to black. That is an R-class radio blackout. And it happens across the entire hemisphere of Earth, facing the sun at the moment the flare peaks. Not in one country, not along one flight path, across an entire hemisphere, simultaneously, without warning, because the X-ray pulse travels at the speed of light and the flare itself is the first indication that it is coming. The NOAA R scale runs from R1 to R5. An R1 minor blackout caused by an M1 class flare produces degraded high-frequency radio communication for roughly 10 minutes on the sunlit hemisphere. An R2 moderate blackout caused by an M5 class flare produces limited radio communication across broader areas for tens of minutes. An R3 strong blackout caused by an X1 class flare produces wide area HF radio communication loss with radio contact failing for about an hour on the sunlit side of Earth. An R4 severe blackout caused by an X10 class flare produces HF radio blackout on most of the sunlit hemisphere for 1 to 2 hours, along with degradation of low-frequency navigation signals for hours. An R5 extreme blackout caused by an X20 class flare produces complete HF blackout on the entire sunlit side of Earth for a number of hours, with no HF radio contact possible and low-frequency navigation signals degraded for days. The forecast attached to AR4420 and AR4425 on April 27, 2026, assigned a 70% probability of R1 to R2 events and a 25% probability of R3 or greater, 25%, 1 in 4, for an event that produces wide area communication loss lasting up to an hour across an entire hemisphere. And the regions producing that probability were not background noise. They were the loudest things on the face of the sun. Here is what the data shows about AR4420, because AR4420 is the central character in this story, and it deserves to be understood exactly. Active region 4420 first attracted serious attention when it developed its beta-gamma-delta magnetic classification in the third week of April 2026. The beta-gamma-delta classification is the most dangerous designation in solar physics. It means that the sunspot group contains at least 3 distinct magnetic polarities, that positive and negative polarities are not cleanly separated but deeply entangled, that there is at least one delta configuration present where sunspots of opposite polarity share a single magnetic penumbra, and that the magnetic field lines threading through the group are under extreme sustained torsional stress, a spring compressed past its tolerance, a knot drawn so tight it cannot hold. The energy stored in a beta-gamma-delta configuration is not measured in megawatts or gigawatts. It is measured in the equivalent of billions of hydrogen bombs, released in seconds, when the magnetic field lines crossing the polarity inversion line reconnect explosively. This is what a solar flare is, not a gradual release, an explosive reconnection. And AR4420, carrying that classification as it rotated across the Earth-facing disk, demonstrated exactly what a beta-gamma-delta region does when it reaches center disk geometry, which is the position of maximum geoeffective alignment with Earth. It fired. M1, 4 at 14:03 UTC on April 26th. M1, 7 at 1924 UTC the same day. M6, 0 at 22:57 UTC. 3 M-class flares in a single day, the last of them the strongest, producing an R2 blackout on the sunlit hemisphere and launching a Type 2 radio sweep at 834 kilometers per second that confirmed the ejection of material from the corona. And observers on the ground tracking AR4420 through filtered solar telescopes reported, in the direct language of amateur science, that the region's unstable magnetic fields harbor energy for X-class solar flares. That was the assessment of independent observers on April 29th, not a forecast. A direct reading of the magnetic structure visible in hydrogen alpha imaging. AR4425 is a name that carries its own history because AR4425 is not a new sunspot region. It is a returning one. Specifically, it is the reappearance of AR4409, the same active region that produced the sustained X-class and M-class activity documented in early April 2026, now completing one full 27-day solar rotation and returning to the Earth-facing disk, carrying the same underlying magnetic complexity that made it dangerous the first time. The Sun rotates approximately once every 27 days, as seen from Earth. When an active region is produced by a deep-seated magnetic structure, it can survive multiple solar rotations, returning each time it completes a circuit around the Sun. AR4409 was that kind of region. When it returned as AR4425, community observers on the Space Weather Live forums noted immediately that it was already announcing itself with C-class flares before it was even fully visible on the eastern limb. One observer described it as likely BGD, meaning likely beta-gamma-delta, before the official classification was confirmed. The observer was correct. AR4425, in its second Earth-facing passage, retained enough of the magnetic complexity of AR4409 to maintain a delta configuration, even as its overall structure showed some signs of the gradual decay that longer-lived regions undergo across successive rotations. On April 30th, 2026, a solar photographer in Santiago, Chile, captured a filtered image of the Sun and wrote that AR4420 keeps intact the gamma-delta magnetic configuration so it can continue to affect Earth from beyond the limb, and that both regions still have unstable beta-gamma-delta magnetic fields that harbor energy for X-class solar flares. That sentence, from an amateur solar photographer in South America describing what he could see through his own filter, is the civilian translation of the same data that NOAA's GOES-19 satellite measures in real time from geostationary orbit. Now understand the system these two regions belong to, because AR4420 and AR4425 are not isolated events. They are products of a solar cycle that has performed far above its initial forecasts, and is now in the phase that the instruments describe as declining, but that the actual flare record describes as something more complicated than decline. Solar Cycle 25 was predicted in 2019 by an expert panel convened by NOAA and NASA to peak at approximately 115 sunspots, with the peak expected around July 2025. The cycle was expected to be modest. Similar to Cycle 24, which was the weakest solar cycle in a century, that prediction was wrong in the most consequential direction. Solar Cycle 25 reached its maximum in late 2024, with activity significantly exceeding the predicted range, producing enhanced eruptive activity that included more than 190 M-class flares and 19 X-class flares during the peak interval alone. The cycle peaked not with the gentleness that the 2019 panel foresaw, but with a level of magnetic aggression that solar physicists are still actively analyzing. And then it began its descent. But the descent from solar maximum is not a smooth slide. This is the part of the solar cycle that specialists in space weather operations carry as a particular concern, because the data, going back through multiple solar cycles, documents a consistent and troubling pattern. The sun does not simply calm down, it stumbles. It fires aftershock eruptions in what solar physicists call the declining phase, complex magnetic configurations that built up during the intense maximum period, finally destabilizing and releasing in ways that are individually more extreme than the average of the cycle would predict. Think of a machine that has been running at full speed for months. The moment it begins to slow is not the moment it becomes safe. It is, in some ways, the moment it becomes most unpredictable. Active region 4366 is the evidence for this pattern that exists from 2026 itself. Region 4366 emerged on January 30th, 2026. By the time it completed its active period, it had produced 21 C-class flares, 38 M-class flares, and 6 X-class flares, one active region, in a cycle that was supposed to be declining. It became what space weather observers described as the most active sunspot of Solar Cycle 25, producing 5 X-class solar flares in only 2 days, including an X8. 3 flare on February 1st, 2026, that caused R3 level radio blackouts affecting shortwave communications across eastern Australia and New Zealand. That was not a cycle at rest. That was a cycle in the declining phase, producing exactly the kind of outlier event that the historical pattern of declining phases documents, and that the initial cycle prediction failed to account for. And the current NOAA 3-day forecast data from May 1st, 2026, even as AR4420 shows some signs of decay, and AR4425 has begun to lose its most complex magnetic configurations, still assigns a 50% probability of R1 to R2 radio blackouts each day through May 3rd, with a 10% probability of R3 or greater events remaining, 50% as a baseline for 3 consecutive days, while the regions are already past their peak Earth-facing geometry. The monthly mean sunspot number for April 2026 was 79.3. The last X-class flare was April 24th. The last M-class flare was April 28th. This is the declining phase of Solar Cycle 25. And it looks like this. Think about who actually experiences a radio blackout when one of these regions fires. Not in the abstract, not as a probability distribution on a forecast page, but on the ground, in the specific places where high-frequency radio is not a historical curiosity, but an active infrastructure dependency. Start with aviation. The global aviation system operates on 2 primary communication architectures: VHF radio for line-of-sight communication within radar coverage, and HF radio for long-distance communication over oceanic routes, where no ground station can receive a VHF signal. The polar routes between North America and Asia, the transoceanic tracks across the North Atlantic, the long Pacific crossings between the Americas and Australia and Japan, all of these use HF radio as the primary, and in many cases the only reliable backup when satellite communication degrades. When an R2 or R3 solar radio blackout occurs, HF radio across the sunlit hemisphere fails. Pilots flying oceanic routes find themselves in a communications blackout where the frequencies they rely on for position reporting, weather information, and emergency coordination go silent. They continue flying. They follow established procedures for exactly this scenario, but the procedures are a managed workaround for a degraded system, not a replacement for a functioning one, and the blackout has no countdown timer. It ends when the ionosphere recovers, which takes tens of minutes for an R2 event and up to an hour for an R3. And during that window, any emergency that requires HF communication is managing with whatever alternative channels remain available. Consider maritime operations. The global shipping fleet, the container ships and bulk carriers and tankers that move the raw materials and finished goods of the world economy across open ocean, relies on HF radio for long-distance communication, for weather routing, for distress signaling in the absence of satellite connectivity. The International Maritime Distress Frequency, 500 kHz, is a low-frequency system, but the working communication frequencies used for ship-to-ship and ship-to-shore traffic in the MF and HF bands are directly affected by radio blackouts. A ship in distress in the middle of the Pacific during an R3 blackout has degraded communication capacity precisely when full communication capacity matters most. The procedures exist, the satellite backup systems exist, but systems that are designed around the assumption of functioning HF radio are, by definition, degraded when HF radio fails. And a 25% daily probability of an R3 event means that over the 3 days of the original 70% forecast window, the compound probability of at least one R3 event occurring was not trivial. It was calculable, and the people calculating it professionally at NOAA's Space Weather Prediction Center were calculating it precisely because the regions producing it had already demonstrated they were capable. Now bring in the second connected system because AR4420 and AR4425 are operating in a solar wind environment that is not neutral. The sun does not fire flares into a vacuum of baseline conditions. The interplanetary environment between the sun and Earth is continuously shaped by the solar wind, by coronal whole high-speed streams, by the remnant effects of prior CMEs, and by the orientation of the interplanetary magnetic field, the BZ component, which determines how effectively any solar disturbance couples with Earth's magnetosphere when it arrives. On April 30th, 2026, as AR4420 was producing its relentless sequence of C-class and M-class flares, NOAA data showed the BZ component turning southward. A southward BZ is favorable for geomagnetic storm development because it aligns anti-parallel to Earth's northward-pointing magnetic field and opens what scientists describe as the magnetopause, the outer boundary of Earth's magnetic shield, allowing solar particles to pour through and drive geomagnetic activity. At the same time, NOAA imagery showed two large coronal holes on the sun's face, one rotating in from the northeast and one facing Earth directly, both producing high-speed solar wind streams expected to reach Earth around April 30th to May 1st. A high-speed stream from a coronal hole arriving at Earth when the BZ is already oriented southward can drive geomagnetic storms independently of any flare activity. And when a flare-driven CME and a coronal hole high-speed stream arrive in close succession, their combined effect is often more intense than either would produce alone. The space weather environment around Earth right now is not a single event. It is a layered condition. The flare risk from AR4420 and AR4425, the arriving high-speed stream from the coronal holes, the southward turning BZ. These are not three separate stories. They are one story about an electromagnetic environment that is under sustained stress from multiple simultaneous sources. Consider a specific morning in this environment. A morning like April 26, 2026, when the sun had already fired an M1, 4 and an M1, 7 in rapid succession before most of Europe was awake, and then fired an M6, 0 at 22:57 UTC, when it was late afternoon on the United States East Coast and morning of the 27th in Asia. The M6, 0 produced an R2 radio blackout, moderate on the NOAA scale. The radio blackout classification that corresponds to limited HF communication for tens of minutes. Think about what tens of minutes means in the specific contexts where HF radio is the active communication channel. A pilot on a transatlantic crossing reporting position to Shanwick Oceanic Control. A fisherman in the Bering Sea attempting to reach a Coast Guard station. A military communications officer using HF for a scheduled contact window. An emergency response coordinator in a region where satellite phones are unavailable and shortwave is the backup. Tens of minutes is not long in the abstract, but tens of minutes during which the communication channel you are depending on is absorbed into an ionosphere that has been hit by X-ray radiation moving at the speed of light, with no warning that was issued before the X-ray arrived, because nothing travels faster than light, and the flare itself was the announcement. Tens of minutes in those circumstances is exactly as long as any emergency that happens to coincide with them. The monitoring infrastructure tracking AR4420 and AR4425 is the most sophisticated ever deployed for this purpose. NOAA's GOES-19 satellite, launched in 2024 and positioned in geostationary orbit 35,786 kilometers above the equator, monitors the sun's X-ray output continuously, detecting flares at the speed of light. NASA's Solar Dynamics Observatory captures images of the sun's surface in 11 different wavelengths simultaneously, updating every 12 seconds, at a resolution fine enough to track the movement of individual magnetic flux tubes within a sunspot group. The SWFO L1 spacecraft, which completed its final orbital insertion at the L1 Lagrange point in January 2026, provides upstream solar wind monitoring at the gravitational balance point between the Sun and Earth, approximately 5 million kilometers away. These systems work. they detected the April 24th X2, 4 and X2, 5 flares. They measured the Type 2 radio sweeps. They tracked the CME trajectories and issued impact forecasts. The 70% radio blackout probability was not guesswork. It was the output of rigorous, data-driven operational forecasting by scientists who monitor the system as a professional lifetime commitment. And yet, the M60 that fired at 22:57 UTC on April 26th from AR4420 produced its radio blackout at the speed of light, 8 minutes after the X-ray pulse left the sun's surface. The warning systems detected the flare as it happened. The blackout was simultaneous with the detection. There is no interval between a flare beginning and its X-ray pulse reaching Earth, in which a warning can be issued and acted upon. The light is the warning, and the blackout is the consequence arriving at the same moment as the knowledge that a consequence is coming. For geomagnetic storms driven by CMEs, the warning time improves significantly. The CME takes 1 to 3 days to reach Earth from the Sun. The SWFO L1 spacecraft at L1 can measure the CME's magnetic field orientation somewhere between 15 minutes and an hour before it strikes Earth's magnetosphere, providing the critical BZ measurement that determines storm severity. That 15 to 60 minutes is real. It is enough time for grid operators to take protective action, for satellite operators to switch operating modes, for aviation to reroute away from the highest risk polar corridors. But for radio blackouts, for the instantaneous X-ray pulse of a solar flare, there is no advance warning that arrives before the consequence. The monitoring is in place, detection is real, the forecast probability was 70%. And the flare that produces the next R3 blackout will be detected, documented, and reported at exactly the same moment that every high-frequency radio channel on the sunlit hemisphere of this planet goes dark. The 7-centimeter radio flux, the standard daily measure of overall solar activity, read 128 solar flux units as of recent readings from the Penticton Radio Observatory in British Columbia. A quiet sun during solar minimum produces readings in the 65 to 70 range. You are looking at nearly double the baseline. This is not a resting sun. The monthly mean sunspot number for April 2026 was 79. 3, the last X-class flare was April 24th, 2026, producing simultaneous X2, 4 and X2. 5 events. The last M-class flare was April 28th. Since the cycle's most active period, a single region, AR4366, produced 6 X-class flares in a 2-day period and 38 M-class flares across its active period, making it the single most productive active region of the entire cycle. AR4409, which returned as AR4425, was the dominant active region in the early April 2026 period and has now completed its second passage across the Earth-facing disk. AR4420, still retaining its beta-gamma-delta configuration as it approaches the western limb, is continuing to produce C-class and lower M-class flares. The current NOAA 3-day forecast for May 1st through May 3rd assigns 50% daily probability to R1 to R2 blackouts and 10% daily probability to R3 or greater events, down from the 70% and 25% of the peak period, declining. But declining from a base of sustained, elevated, complex solar activity produced by regions that have not finished rotating in a cycle that has already demonstrated its willingness to produce events well beyond its predicted range, in a declining phase that the historical pattern says is where some of the most damaging individual space weather events of any cycle have occurred. The system is not dormant, it is awake. And 2 complex regions, one of them a returning veteran of the most active solar period in years, are still on the Earth-facing disk as of this morning. They are showing decay. The magnetic configurations are simplifying. The flare probability is decreasing. This is what the data shows. The data also shows that AR4420, as of April 29th, still retained its gamma-delta magnetic configuration, which means it can continue to affect Earth from beyond the limb as it rotates out of direct Earth-facing geometry. A flare from a region behind the western limb of the Sun, while less likely to send its CME directly toward Earth, still sends its X-ray pulse at the speed of light in all directions simultaneously. An X-class flare from a region behind the limb still produces a radio blackout on the sunlit hemisphere. The geometry changes the CME threat. It does not change the instantaneous electromagnetic threat. And behind AR4420, as it rotates toward the limb, new regions are rotating into view from the eastern limb. The Sun has been producing active regions continuously since the start of the cycle maximum. The current surface of the Sun shows 7 numbered active regions. 2 of them have dominated the past 10 days. What rotates in next is unknown until it is visible. What is known is that solar cycle 25, despite its official designation as being past peak, is producing more total activity than its 2019 forecast predicted, in a declining phase that is behaving more like a sustained plateau than a descent. Somewhere right now, a pilot crossing the North Pacific on the Great Circle route between Tokyo and Los Angeles is listening to the static on an HF frequency that was clear 6 minutes ago. Somewhere, a maritime radio operator on a bulk carrier south of Greenland is rekeying a frequency that has gone flat. Somewhere, a radio technician at a remote research station in Antarctica is troubleshooting a communication link that has failed without obvious cause. These are the human faces of an R-class radio blackout. Not dramatic, not cinematic, quiet failures, frequencies going flat, channels going dark. The ordinary administrative infrastructure of a civilization that has built itself around electromagnetic communication becoming, for tens of minutes, unreachable across an entire hemisphere. The people experiencing it know their procedures. They switch to alternate frequencies. They try satellite channels. They wait. And most of the time, the ionosphere recovers and the channels come back and the moment passes as a logged entry in a communications record that no one outside the professional space weather community ever reads. Most of the time. The NOAA forecast for the current window is 50% probability of R1 to R2 blackouts, 10% for R3 or greater, 1 in 10. Those odds are not zero. And they are attached to sunspot regions that have already produced 4 M-class and 2 X-class flares in the past 10 days. Regions that carry magnetic configurations that a photographer in Santiago, Chile, could see through his filtered telescope as unstable and dangerous. Regions that NOAA's GOES 19 satellite is watching right now, at this exact moment, at a temporal resolution of 12 seconds per image, for the first sign of the next explosive magnetic reconnection event. The monitoring is in place. The detection is real. The 70% has declined to 50%. The 50% has not declined to zero. And the sun does not consult the forecast before it fires.